Okay, so let's start the class. So I have posted an assignment which is due next Wednesday. So you have two attempts. For the first attempt, you want to try to do it without looking at hints. And second attempt, then you can look at the hints. Right? The first assignment is very easy. I think it's due on Wednesday. And I highly recommend that you work in a study group, not with WhatsApp, but in person. You make connections, connect with people around you, and you can work together. The other thing for the textbook, we're going to start not by electrostatics, but we are starting with electric circuit. So make sure you go over the unit and start reading over and work on the problems. Is that clear? Oh, I forgot to tell you, bring a TI. TI 30 or TI 8384. Or any TI or any scientific calculator as long as you know how to use it. Okay. I just want to make sure you understand the concept before doing all the math. So here you have, let's go to my simulation. So this is called what? What do we have here? The battery, which is a power supply. Okay, so you're going to have some chemical reaction inside. So chemical energy will be converted into electrical energy. And this is called the load. Very good. So this is producing energy, and this one is consuming energy. So the way you want to think about it here, even though it's not really what's happening, imagine that all those little arrows here, each one of them is 1 coulomb of charge. Okay, so coulomb is a unit for charge. So imagine you have 1 coulomb of charge flowing. So we need connecting wires, right? And each coulomb of charge will have a potential energy of 9 joule. Okay, so 9 volt means energy per coulomb. Volt is a potential energy, so the voltage is potential energy. So we have 9 joule per coulomb. Okay, so then those little coulombs bring the energy to the load that turn that energy into light and heat, and then they come back here to the negative terminal, negative side. So this is positive, this is negative. So you see the current always flow from positive to negative. And I told you this is not really what's happening. What's happening, it's actually electrons flowing, not positive charges. Okay. In addition to that, electrons are not really flowing from negative to positive. What's happening is more like I don't know if you remember from last semester, something like this. Remember the conservation of momentum? So that's what's really happening with the electron. They push a little bit each other out. Okay, but just to make sure we understand what's going on, we're going to pretend it's positive charges moving from plus to minus. And each time they go back to the power supply, they get a boost up. Okay, so they get their energy raised to 9 joule again. These 9 joule here are delivered to the load, and it keeps going. Now then, we talked about the amps. Okay, so the current. So usually the way you measure current, you have to open the circuit. So I have to open the circuit here and have my multimeter as part of the circuit. So it doesn't matter where you place it, but I'm going to place it here. But you can place it anywhere as long as it's part of the circuit. So let's increase here the voltage. So what does it mean here? The current is 2 amps, which means you have 2 coulombs of charge. Okay, so 2 coulomb every second flowing through it. Okay, so it's like something is counting. So it says, okay, during 1 second, I have 2 coulombs of charge flowing. Or you can say every second the power supply is producing 2 coulomb of charge every second. Okay, so what is the current? You can think of that as the amount of charge flowing per second, or you can think of that as like a rate. So it means if you increase the voltage here, you see how it's flowing faster? So because it's flowing faster, the energy is delivered faster. So of course, it's going to be more energy delivered per second. Is that clear? Okay, it's like a slow metabolism, high metabolism. Okay, that means someone old like me, someone young like you. Okay, it's the rate at which energy is consumed. So let me ask you something. If this is 60 volt, okay, so 60 joule per coulomb, and you have 6 coulomb per second. So what's going to be the energy delivered per second? So 60 joule per coulomb, and you have 6 coulomb per second. So every second, how much energy is going to be produced or consumed? 360, right? So 360 joule per second. That's what we call the power. Okay, so power is the energy produced by the power supply or the energy consumed by the load every second. So you have two ways in this circuit to increase the amount of energy delivered. You can increase the voltage, obviously. You see, it's going to run faster, or the current, when the current increases, you have also more energy. So in that case, you can only control it by the voltage. Is that clear? So current is charge coulomb per second, and the voltage is energy per coulomb. Okay? Now, is it going in one direction only, or is it going back and forth? One direction. That's why it's called DC, direct current. Okay, so direct current is when you have a battery, for example, or a power supply, DC power supply, and the current only flows in one direction, which is not the case when you have voltage from the grid, here from the outlet. This is not DC. That means the current, okay, flowing into my laptop, for example, before it gets converted to direct current, the current that I'm getting from the outlet will be AC. So it's going to go back and forth, back and forth, back and forth. So it's alternating current. From a battery, it's only DC, direct current. Is that clear? So if you want to measure the amps, okay, that device here, ammeter, has to be part of the circuit. If you want to measure voltage, okay, and we're going to do that today, you take your device, okay, you don't touch the circuit, you let the current flow, and you see here you're going to measure what we call the voltage drop. So you are measuring it. Measuring voltage is like measuring height. Okay, so it's like measuring height. So you have 15 volt. That will be your voltage drop. Is that clear? If you want to measure, of course, the voltage drop across the load, energy is conserved. So what do you expect to have? 15 volt. Does it make sense, right? Does it make sense or no? So let me ask you something, just since we are here. I'm going to open that. I'm going to take another load here. And okay, I'm going to change the value. So what is the voltage drop here? 15. Okay, let's find out what's going to be the voltage drop. About 2.68. Yes, volt. So what do you think the voltage here across here? What is it that you're going to do? So you start with 15, you drop by about 3. So how much is left? 12, about 12, right? See? So these are called voltage drop. So you have to think of that of height, like height. You start with 15 volt, boom. You fall by 3, boom. You fall by 12. Okay, so it's really electricity 101. Now, if you think, so you don't have choice, you have a power supply and you see it's going too fast, okay, this is too bright, and you want to slow down the current because you cannot change the voltage. You know, in a battery, you cannot change the voltage. Obviously, it is what it is, right? So for that, we have a special component. We call that a resistor. And a resistor, what it does, okay, it's take the circuit, it's like a pipe, imagine it's pipe, okay, with current flowing, and it's going to squeeze the pipe all over, everywhere, right? So let's see if it works. I'm going to open that. I put my resistance or resistor here, and now it's going to, so if I increase the resistance here, do you see how it's going to slow down? Slow down. Okay, so we have 3 physical quantities. 1, 2, 4, actually. So you have the voltage, okay, which is the energy per charge. So it's like a pressure, right? It's pushing the charges in the circuit. Here we have the loads, and we also have a resistance. So we'll talk about that later. But you have the current in amps, and you have the resistance here in ohms. Okay, so don't worry about that. We'll see that later. Another thing to see is that the current does not leak out. Okay, it goes from plus 2 back to minus, right? So it goes from here, which is 70 joule per coulomb. The energy is being delivered to the load. And when the charges come back here, they do not have any energy left, so they get a boost again. So it's like a hydraulic system, as we discussed last time. Okay, any question? So once you understand the concept, then it's easy. It's not so hard. So let me see here. I brought a demo for you. Hello. So this is the power supply. I have 3 batteries in series. Each one of them is 1.5. Okay. So tell me your name if you participate. Okay, so 1.5, 1.5, and 1.5, that will be 4.5 volts. Okay, and I'm gonna have my load, and you can see I'm gonna skip the switch. So what does it mean? It means that each coulomb of charge, so this is plus, this is minus, each coulomb of charge is raised to how much energy? 4.5 joule. Each coulomb of charge. They are flowing here from plus back to minus. You have some chemical reaction, and each charge gets some energy again. Okay, so it's like they are being raised to a higher level of energy. That energy is delivered here, and then they come back with no energy. So you see that if I decrease the voltage, what do you think is going to happen? If I have now 1.5 and 1.5, that will be 3. Okay, so you see you have less pressure, so the current cannot flow as fast, so the load does not get that much energy. I can decrease the voltage even more. Now I have only 1.5, and you see it's not very bright because I have only 1.5 joule per charge. Is that clear? Now I can measure the current. So to measure the current, I need to open the circuit, and I have this old device. This is analog. So nowadays we use something like this, which is a multimeter. It's very cheap, but that's the old way. It's analog, but that way you can see what's going on. If I have to go to minus, so this one has to be connected to minus here. It says minus. Okay, you see nothing happens because I didn't close the circuit. So I close the circuit. And can you see it move to here? Right? So that will be, I need to look at that scale. That will be the amps. Unit is amps, amperes. And it says about 0.3 amps. So that means that through that device, you have 0.3 coulombs of charge, or 0.3 coulombs flowing through it every second. Or you can say you have 0.3 coulomb being produced by the battery every second. Is that clear? So I can find the power delivered. Okay, the power is the voltage. In that case, you have that voltage here multiplied by the current. That will be your power. Is that clear? So if you decrease, of course, the power supply, you see you're going to have less current. And if I decrease even more, you even have less current. I have about 0.2 amps. So usually we don't use amps when it's so small. We use milliamps. Okay, so 1 amp is 1,000 milliamps. So 0.2 times 1,000 is 0.2 times 1,000, 200, yeah. So 200 milliamps. Is that clear? Okay, so we'll get back to that. I just want to make sure everything I said. And again, it's DC. Okay, so it's flowing only in one direction. Okay, so you see, you need to it's okay. You have to make a circuit, okay, from plus to minus. Okay, so let's go back to the slides. So for example, typical example that you are familiar with, here you have the battery. So the battery inside your car is how many volts? 12 volt. So every coulomb of charge will be raised to an energy of 12 joule. Okay, and you need that when you start your car because the wheel, is very heavy. It has a lot of inertia. So you need like a starter. Okay, you need something to start your flywheel so it starts to run, but very smoothly. So you need that battery here. You need to have a large current. You use that current as well for your spark plug, for example, for your lighting or anything electronics in your car. And then you are driving, the battery will charge again, recharge. Okay, so what's wrong compared to here? What's the difference between here? So you see here, you have a circuit, the demo I did. What's the difference with that? What is it missing that you don't see? Hmm? So here you have plus, deliver the energy, go back. Do you see a closed circuit here? So how do they come back to base? What is it that you are using here? So no, it's DC, but you need a way to return to base, right? You need a return path. And instead of using a wire to return to base, they use the chassis of the car. Okay, so the chassis of the car is made of metal, and that will be your return path. Okay, So they use the car itself as a way to go back to base, right? So you still have a full circuit. So we're going to see it's called a parallel circuit. So all the loads are in parallel, and we're going to see why. But the way they come back, they use the chassis of the car. Okay, so the chassis of the car is going to be like your ground. Is that clear? Okay, so here the same idea. If you make a circuit, so here you have a 1.5 volt battery, you want to make sure to make a circuit. So if you do this, it's not going to work. That will not going to work. This one will work because it goes inside, goes here, chuk, 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 and go back to base. Okay, so here are some definition, some equations, and I will talk about them very soon. First, you have voltage. What is voltage? The unit is volt, so it's named after Alexandro Volta. So voltage is the energy per coulomb. You can think of coulomb like a little marble, right? Little sphere, and each sphere is 1 coulomb. So every single coulomb being produced, okay, burnt out by the power supply has an energy equals to the voltage. Okay, so the voltage is the energy per charge. If you are asked, to plug numbers to find the voltage, okay, equals to energy in joule divided by the charge in coulomb. Notation for charge is Q. Okay, so if you so that will be your equation. I will define them. And by the way, you need to remember to print out the equation sheet so you can get familiar with all those equations. And then we have the current. Okay, how do we define current? So unit is amps or ampere. Okay, it's named after ampere. So notation is capital A. So the current is the amount of charge per second. How many of these little coulombs will flow, okay, in the circuit per second? How many of those little marbles marked 1 coulomb are burnt out every second by the power supply? So you see, it's the charge in coulomb divided by the time in seconds. So it has to be second. So equation will be the current notation is I, capital I, equals Q over T. Is that clear? And then I will introduce later another physical quantity. We call that the resistance. Okay? And the unit is ohm. So resistance is that little component I show you that is used to limit the amount of current, okay, to make the charge move slower so the energy delivered is not that large. So it will limit the current for a given voltage. Of course, you have the electric charge. So that's a property of matter. Okay, like mass is a property of matter, charge is a property of matter, and the unit is coulomb. C. So you have positive charge, negative charge, but only remember the electrons can move. The positive charge will not move. So if an object is positively charged, that means it's missing electrons. If an object is negatively charged, it's because it gained electron. Okay? So we'll see that more in details in the next unit about electrostatics. And then you have the electric power. Okay, so it's energy produced by the power supply per second, or the energy consumed by a load per second. The unit is watt. Okay, so energy divided by the time. And if you want to find the power, for example, consumed by a load, like a microwave, for example, is a 1500 watts. That means your microwave is consuming 1500 joule per second. So microwave, as you all know, has a lot of appetite, so you don't want to run it like all day long. Hair dryer also lot of power, a lot of energy consumed. So anyway, the energy consumed by a load, like a hair dryer, will be the voltage drop across that load, which is 120 volt, for example, times the current going through it. Okay, we'll go in more details as just an introduction. Is that clear? So that's why you need to understand everything electricity, because if you work in hospital or any domain, you need to have some background so you don't get electrocuted. So here, for example, again, I have my car battery. So it's 12 volt. So 12 joule per coulomb. So let's say I have 4 coulombs every second. So that means the current will be 4 amp. Every single one is holding 12 joule. Okay, so every second, how many joules are there available? 48, very good. Okay, so that will be the power energy available every second, produced and then consumed. So the current is 4 amps and the voltage here is 12 volts. I have only one load. So whatever the voltage here will be whatever the voltage here. So we call that a voltage drop. So again, the current, you imagine those little coulombs of charge. Okay, so 1 coulomb, 1 coulomb, 1 coulomb. And it's crossing that cross section every second. Let's say you have 3. So that means 3 amps. Okay, do you understand how it works? So it's not that hard. So let's talk about voltage. Okay, so voltage is like we talk about voltage drop. Okay, so it's the amount of energy per coulomb. So you have all kind of, and I will show you right now. But for example, you have the car battery that will be 12 volt. This one is 9 volt. So when we were a kid, I don't know here, but in France, we would take those battery, put that on the tongue, and tingling, right? Because you make your tongue is a conductor, so you will have electricity flowing through your tongue. It's totally safe, okay? It's not enough current to kill you. So this one is 6 volts. So let me ask you something. And you know the batteries here? You're all familiar with, you have AAA, AA, C, and D. And they are all what? What's their voltage? 1.5. But you know that for the heavy load, you're going to use a D, for example, for a toy car. And for your mouse, you're going to use a small one, a AAA. So what's the difference between them? What's the difference between a big C or D battery and a AAA battery, even though they all have the same voltage? Like this one is 6 volt, this one is 9 volt. You can use this one for your camping lamp, but you are not be able to use this one even though it has more voltage. So what do you think is the difference? So this one can provide more energy than that one because so you have voltage and you have current. So the big one will have the same voltage, for example, than the AAA, but they will be able to produce more current. So for the same voltage, if you have more current, that means more power. Why is that? It has to do with the chemical reaction going on inside. Okay, so you have more juice and more stuff inside, so you're going to produce more current even though the voltage is the same. So those big long-term battery that I have here, I have one there. Here, you see 6 volt. They are designed for a lamp. Okay, so it's for camping lamp, right? Because a lamp needs a lot of current. So even though the voltage is small, the current will be large, right? But if I do that, I don't feel anything, okay? Because my hand here provide enough resistance. Okay, so let's show you. So first of all, this is something the might have to use one day. Okay, so this is a voltmeter, multimeter, so it can measure voltage, it can measure ohms, that means resistance, it can measure amps here. Okay, so for example, M means milliamps, 10 means 10 amps, the maximum. Okay, so I'm going to put in voltage to 20. So what you do here, okay, you have your probe. This one goes to positive. The black, it's always in COM, which means common ground. And what's the reading? Very good. So it means it has lost some voltage. It's supposed to be 4.5. Now, if I have only the 3, so that's 3, that's 2. How much you read? About 2.95, right? So it's even less, of course. Okay, so that will be called the voltage drop. And then here I have about 1.47. Okay, so it's supposed to be more than 1.5. Usually they give you a little bit more than 1.5. And these are the expensive ones. So if you buy one at the dollar stores, it won't be the same. Okay, it will be cheaper. It's not the same stuff inside. So it's not going to provide you with the same amount of current. Okay, so there is a reason why you pay more. Okay, so this is what you expect this one to be. 6, right? So it's called the voltage drop. So I go from plus, one is plus, the other one is minus, and you get 6.54 volt. So it means each coulomb of charge leaving the plus, going to the load, back to the minus, will be given how much energy? 6 joule, right? I just bought it for the class. And here another example. So these are the big ones. So it's a C. And you see it says somewhere plus. Can you see the plus? And here it's a minus. So that's important because sometimes some loads are polarized. So it means one side has to go to plus, the other side has to go to minus. And if I measure it here, I have about 1.5. So if I ask you, for test one, double A or C, they have the same voltage, but they don't provide the same amount of current. Very good. So it means more power. Okay, so that's why they are also more expensive. So here I have a 9-volt battery. Let's see. So one is plus, the other one is minus. And you have about, do you see? 9.5, right? 9.5. Okay. The minus doesn't matter. It's just if I touch the plus with the black, you have a minus, but it doesn't really matter. And here I have what you expect. I have 1.5. I have cheap dollar store batteries. So 1.5, 1.5, 1.5, 1.5. Huh? About 6, right? So let's see. They are in series. So let's see if it works. 5.7 volts, right? Are you with me? So that will be a voltage drop. You have other ways um, to make current. So for example, you can have, what is it? What is that thing? Solar panel, right? A solar cell, right? And it will turn energy from light into electrical energy. Okay, so you are using energy inside those photons, so from light, and that will be turned into a voltage. And so I bought this one from China, and it doesn't work, but I use it for a demonstration. So the way it works, you have cells here. So 1 cell, 2 cell, 3 cell, 4 cell. Each cell is 0.5 volt always with full light. So let's see if it works. I know if that light will work. And you have about 1.5. So there is no current, there is no electricity here. Okay, it's just a solar cell. I can have I don't know where it is. Yeah, I can have a load. So no electricity here, just the solar cell. Except that this one I have to be careful because it's polarized. I don't know if you can hear. It was working. Ah, can you hear? Now if you it's not very strong, but if I have a light bulb, can you hear? And then do you see how it gets? Isn't that cool? So this is called the inverse square law. If you multiply the distance by 2, energy will be divided by 4. And you can see that with the sound. So it depends on the amount of light, and you use the energy from the sun. Okay, any question? So the inverse square law of motion, we'll go back to that, but you see you have light here. Okay, so the energy from the light spread out in space. So if you have a sensor here, so you measure the amount of light that you're going to collect. If you multiply the distance by 2, okay, that same amount of light will spread out over 4 times the area. So the light, if you multiply the distance by 2 from the source, here it will be divided by 4. If you multiply by 3, it will be divided by 9. Okay, and so forth and so on. And it works the same for gravity. So if I am 400 pounds, okay, from the center of the earth, I am 400 pounds on the earth. Now I'm moved at a distance twice as large on the earth, twice. So that means my weight will be 100, okay? You multiply distance by 2, the weight is divided by 4, okay? So it's called the inverse square law. Okay, so remember the experiment by, I don't know if, okay, I have to do this. Luigi Galvani, right? And it was Volta who understood how to make a battery. To make a battery, you need two, and I think it's a pop quiz question, you need two types of metal, okay? It has to be two conductors, and in between, you need to have some kind of juice, electrolyte, even water. There is so much stuff inside water, it will work also, okay? And that's called the oxido-reduction reaction. So I cannot tell you the details because, you know, chemistry and me, we were not very friends, but you should know better than I do. So anyway, you have some chemical reaction in there. One is giving out electrons, the other one is gaining electrons, and at the end, one electrode will be positive and one electrode will be negative. So for example, if you have copper and zinc, okay, copper will become the positive terminal and zinc will be the negative terminal. Very good. So here is an easy demo that you can do if you want for your demo. You can take two potatoes, Okay, you have zinc. This is zinc, and this is copper. And why do we attach them like this? With what is it called? A battery in series, right? So that way you multiply the voltage by 2, and then you have your own battery. So it's usually done with potato, but you can do it with lemon. That works also. And that was the genius of Volta. That's what he did. He took copper and zinc. In between, there was some like a cardboard or fabric that was wet with brine, which is salty water or acid. So that was 1 volt. And then keep piling up. So 1 volt and 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 1 volt. Okay, so that was the first battery. So in your car battery, it works the same way. So one cell is 2 volt and you have 6 cells. So how much is that? About 12 volt. That's how it works. So I brought a demo. So I don't know if it's going to work, but we can try. See, I am the only one to do demo because it's very embarrassing to do demo and it doesn't work. So this is my potato. Plus it's an expensive potato. See, it's a sacrifice for science. So you have copper and zinc. Oh, sorry. Thank you. Okay, so can you see? So you have 2 potatoes, okay? I'm not trying to trick you. These are purple potato, the good one. Okay, so I have zinc and copper. So I'm gonna put them inside. They should not touch. Okay, so you have 2 conductors, 2 different metal. One will give out electrons, the other one will gain electrons. So you have some oxidoreduction reaction inside. And at the end, can you see here? Okay, so at the end, I should be able to get some voltage. So let's see. This is plus, this is minus. It's not much, should be a little bit more. So what do we get? Ah, that's good. So what do you see? 0.9, 0.8, about 1 volt. Okay, it's not stable because chemical reactions are always happening. Okay, but that's not enough to power anything. So I'm gonna add another one. So I'm gonna put this is the copper, has to be juicy, they cannot touch each other. This is both copper, so they won't work. So then I have another one here. I'm making a mess. So how do I connect them now? The what? I need to use a wire, but which one I have to connect together? The plus here with the minus. Okay, so now I have a battery in series. Okay, and if I measure voltage, oh, look at that. Do you see? 1.8 volt. So it's twice as much as before. Isn't that cool? And if I take a load, so this is my load here, it's polarized. You see, red goes to plus, right? Can you see? You see or no? Yes. It's 12. Isn't that cool? Incredible, right? Imagine the breakthrough at the time. They were able to produce electricity, to produce voltage without the hassle of a Leyden jar. Okay, so now you can control electricity. You can also lit LED. I have a small LED here. It wants to come. So I have a small LED. So LED is a semiconductor. So a semiconductor, uh, that means that it works with quantum physics. So it means you need to give it the right voltage, otherwise the current cannot flow through it. And it has a long leg and a short leg. And the long leg will have to go to the plus, so it's polarized, and the short leg has to go to the minus otherwise. And it doesn't work with one potato because it needs at least 1.6 volts. So I don't know if it will work. Ooh, do you see? You see that? Huh? Isn't that cool? You see, I'm old, but I still find that quite impressive. So anyway, if you want to do like a demo like that, it's not very hard to do. Oh, and then the dangerous thing. Okay, the dangerous thing to do. You ready for that? So, do you remember what did we say? This for the outlet? Alternating current, right? Not DC. How much voltage do you expect? 120 volts AC. 120 volts AC. Not 120 volts, right? So with my voltmeter, I can check this out. Except that you have to put that in AC. You see, you have voltage for direct current, voltage for AC. And then in the outlet, you have three holes, okay? The small one is the hot. I don't know if it says emergency, so I don't know. I'm going to try. The other one is the rectangular, and this is the ground. So let's see. Okay, I need a volunteer. Can you come? That's 121.1. 121.1 volts AC. Okay. I'm not afraid because it's insulator, so I don't take a chance here to say it. I'm not saying that you should do it. Now, the trick is make sure it's in voltage. If it's not in voltage and if you have it in amps, that will be very bad. Okay, you want that in voltage. So the outlet is providing us with 120 volts AC. Power supply here will be DC. Okay? So I'm still alive. Otherwise, we have to have another professor. Okay, so we talked about Humphrey Davy. He's the one who placed like 2,000 batteries in series, and so he was able to make a spark here. Okay, so we already talked about that. And then I think it was a British named Daniel. He came up with the Daniel battery, which is so if you take a chemistry class, have you done that experiment here? Something like this, right? So it's a little bit different than the potato because you see the electrons are not in the same liquid. Okay, so it's much more stable. It works better this way. Okay, and that was called the Daniel cell. So that's the batteries that we use today. But again, it's the same idea. You have one electrode made of carbon, for example, one electrode made of copper, and you have some or copper or zinc, I'm not sure, and then you have a chemical reaction inside. Okay, so this is already, we talked about that. That's how we're going to measure the voltage. So okay, so when you are measuring the voltage, you have to close the circuit first and you are measuring like a voltage drop. So you come from outside. So very, very important to understand that when you are measuring voltage, here there is a very, very large resistance. So almost no current will flow through it. So that's why I didn't get in trouble here, because even though the voltage was 120 volt AC, which is quite dangerous, the current didn't flow through it because the resistance is very large. But if instead you put in amps, okay, so instead of voltage, you put here in amps, that will be very bad because then there is no resistance, the current flow through it, and I don't know, I would jump out or something like this, I will be electrocuted. So you want to make sure that you are measuring voltage, the knob has to be in voltage. Okay? So voltage is very much like altitude. And it's not because when you make a circuit, okay, so maybe you have a circuit in your house, it's not because the microwave comes first that it will take all the voltage. It depends on their appetite, okay? So if the microwave takes everything, if you have your loads in series, nothing will be left for the other ones. So let me explain what I mean. So for example, here I'm going to increase this one. Okay, so this one, no, I'm going to do the opposite. I'm going to decrease, no, I'm going to increase this one, decrease that one. Maybe I'm going to put a large voltage here. Okay, 120 volt. So you see I have two loads. Let me remove this one. Okay, so I have two loads. Can you see? Okay, so what's the voltage drop available? That's going to be 120. Okay? So you might think this one comes first, so it's going to take more voltage drop. No, it doesn't work that way. Okay, so I'm going to measure the voltage drop. It's about 50 volt. How much is left for the other one? Right? So it will be 120 minus 50. And it's going to be about 70. Okay, so it's not because this one is placed first that it's going to take more voltage. We're going to see it depends on the resistance. Is that clear? So you have to add up the voltage drop. So imagine voltage like a drop, right? You start with 120, boom, you fall by 50, and then boom, you fall by 70. Is that clear? And if I add another load, so this is another load here, a resistor is there to decrease the amount of current, but it's also a load. So this one now has only 66, and this one has its own voltage drop, which is about 6. Okay, so if I add this voltage drop plus that voltage drop plus this voltage drop, I will get 120 volt. Is that clear? So this is called a circuit in series. Okay, so a lot of applications, since you are in science, you all familiar with EKG. So what are they doing? They are measuring voltage. And the thing that you have to remember is that voltage is a property of 2 points. Okay, it's always the voltage relative to what? So for example, if I take 6, I have a 6 volt battery. Okay, so the plus is at 6 volt above the minus. So it's always 2 points. So when you are measuring the voltage drop, it's always across 2 points. That's like a drop. So here, that's what they are doing. They measure the voltage between A and B, or between one of them is the ground, so between A and C, or between D and E. I'm not sure how it works, but that's an application for that. So you're measuring voltage, okay? because our body is like an electrical system. You have also something called EEG. Same thing, you are measuring voltage. So you have electrodes here. So you're measuring the voltage drop between this point and that point. And then here at BBC, they have the lab and they do all kind of experiments with this weird thing on your head. So you are also measuring voltage. So what they do, they make you go for exercise and then they see what's going on in your brain. So it's a lot of electrical activity in the brain. Is that clear? So don't ask me what is it doing here, I forgot. Maybe because last semester we talked about cancer. It's a very nice book if you are interested. I lost a loved one to cancer, and this book is by Thomas Seyfried, and it's a small book, but it explains everything, okay, and different way, not holistic, but different approach to deal with that. And I forgot who is Jim Abrahams. I'm sorry. I really don't know what is doing here. It's just a tangent. Okay, for eyes also, you can take what it's called ERG, and it's also voltage, right? So voltage is a property of 2 points. Is that clear? So that's why you need to know how to measure voltage. And then the current, again, the current is charge per unit second. So for example, here, each coulomb is 120 joule. So if you have every second 3 coulombs being burnt out, so 3 coulombs being burnt out by the power supply, so what's going to be the current? 3 amps, very good. So how much energy is available every second? 3, 120, 120, 120. 360 joule per second. And that will be the definition of watt. Okay, so that energy produced per second will be available for the loads. So when you find, if you compute the energy consumed by this one plus energy consumed by that one plus the energy consumed by this one, it will be 360 because energy is conserved. And then it depends on their appetite, okay? So maybe this one, the current is the same everywhere because it has nowhere to go, but the voltage drop can change, depends on their appetite for energy. So maybe one will take most of the energy and maybe this one will not work. But anyway, that will be the definition for amperes. Okay, so we have direct current and alternating current. Okay, so from the outlet it's alternating. For example, the current from the outlet will go back and forth 60 times per second. 60 times per second, that means 60 hertz. Okay, we'll do that later. So again, when you are measuring current, the first thing you want to make sure is that here you are at the right setting, amps, okay? And your device here will be part of your circuit. So you're measuring 0.53 amps. How much is that in milliamps? Multiply by 1,000. Very good, 530 milliamps. Is that clear? So make sure that will be aimed here at amps. Okay, so that's how we measure current. I don't know if I want to show you or not. Very quickly. It just is such a, it's very important because, of course, everyone has to deal with electric devices, especially if you go to the medical field. So I have my power supply. Where is my load now? So this is my load. So I have to I have to close the circuit. And I have to close it. Up. I need another. Okay. So you see here it says COM, okay, so that means ground. And here it says milliamps. Can you see here it says milliamps? So I'm gonna go to milliamps. And nothing happens, I don't know why. Oh, because I didn't connect it here. And it says 1. What's going on? What do you think is going on? How come I have a 1 here? Because what? No, no, no. I'm trying to measure current, right? I make a closed circuit. My load is happy, it's consuming energy. But here I'm not reading anything. And it says milliamps, but look here, it says, what does it say next to it? 10 amps. So what do you think is happening here? The current is too much. Okay, so it's not in milliamps. I have to go in amps. So I'm gonna move here. I'm gonna move that probe here. You see how it works? And now it's happy. Okay, I'm gonna go to me here. I have to go to 10. 10 amps is the maximum. If you go over 10 amps, you're gonna fry it. And it says, what does it say? 0.33 amps. So how many milliamps? 333. Okay? But to measure current, the thing that you have to remember if you deal with that is that you have to make a circuit. So the charges, when they flow, they go through the device, so it's like something is counting back there. What you don't want to do, and you will get in trouble, I will take points off my students when I was teaching lab, is that what you don't want to do is to have your multimeter here in amps and measure the current with that. That will be called a short. So that will be very bad because you fry your device. Do you understand? So if you want to measure voltage, it has to be in voltage. It cannot be in current. Otherwise, you make a short. Okay. So you see here, your device is part of your circuit. So this is to measure voltage. So we call that a voltage drop. If it is part of your circuit, you are measuring current. Okay, so it's not the same. Here you are measuring voltage. Here you are measuring current. That's why it's called a multimeter. Okay, so the electric current we imagine, okay, because it's easier to understand, that you have positive charges like Coulomb flowing when actually it's electrons really moving a tiny bit. Okay, so this is called the conventional current, right? Goes from plus to minus. Okay, so the equation so far, we have time elapsed. Unit will be in second. We have the energy consumed or produced. The unit is in joule. We have the amount of charge. The unit is in coulomb. You have the amount of charge per second. So that will be the current, right? So it's Q over T, coulomb per second, and the unit is amps. We have the voltage, which is a property of 2 points, okay? The unit is volt. We have the power, unit is watt, and it's energy per second, okay? And V equals, the power is V times I, And coming up, we're going to talk about the resistance and the unit is ohm. Okay, so now you can talk to each other, help each other out, and we're going to answer those questions. So first, think a little bit, talk to each other. And remember, we have a pop quiz, so make sure to bring a laptop or something like this, so guys. So let's try to measure the first one. The current is A, very good. 2 volt is the unit for voltage, that's easy. Ohm, resistance, yes. Power is C, energy per second. It's power, think metabolism. How fast you are consuming energy, how fast energy is produced. So that's power. Unit is watt, named after James Watt. Voltage is energy per charge, very good. So it's a potential energy per coulomb. 1 amp is same as D, 1 coulomb per second, okay? Amp is coulombs per second. How many charges crossing a section per second? 1 volt is C, very good. A coulomb of charge that passes through a 6-volt battery is given 6 joules. Okay, what is correct? A. Okay, so the current flow through a circuit. And okay, so if you have 24 joule, okay, for 10 coulomb, so the voltage supplied will be A, very good, okay, joule per coulomb. So each coulomb will get 2.4 joule. If you have 10 coulomb, zoom, 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 going through, your multimeter for 10 seconds, the current is 1, okay, because it's coulomb per second, okay? So if you have 10 little charges for 10 seconds, so that means you have 1 charge or 1 coulomb per second. So the resistance, I told you, is like you have a hydraulic system and you squeeze the pipe, right? So it's like you're limiting the amount of current, like you are limiting the amount of water flowing. So you can do that with a C valve, right? You can close the pipe or open the pipe. Okay, so that's a electric power equation is you multiply the voltage drop by the current through what? Through the load. So the power consumed by a load equals to the voltage drop across the load times the current going through it. By the way, like in a house or an apartment, the maximum current will be 20 amps. If you try to drain more than 20 amps, you know you have the fuses, okay, because you don't want to start a fire. But usually 10 amps, 20 amps is the maximum. Energy, okay, so V equals E divided by Q, or you can say that the voltage equals E divided by Q, or that's just the same thing. And you have this equation here. So the same equation, okay? What's the difference between D and the triple A? And do they have all the same voltage? Yes. What's the difference? Current. Very good. Excellent. Very good. Okay, let's try to do this one. Oh, am I good with the time? Yes. Okay, so you can help each other. And let's try to do this one. and don't stare, okay? Try to do it. So the current in a 3-volt battery, so that will be the voltage drop, is 0.17 milliamps. Okay, so that means the current, I'm not happy with milliamps. I'm going to convert that to amps. So 1, 2, 3. So that's going to be 170 amps. Okay, in 1 hour, 1 hour. So 1 hour will be the time. So first thing, you want to identify all the physical quantities. Make sure you have the right units. So you don't want milli, you want amps. And the time, are you happy with 1 hour? No. Okay, so you convert that into seconds. Okay. And then it says how much charge. So it means charge is question mark. Okay, so you can look at your equation or your equation sheet that you are supposed to print out or just remember how it works. Which equation can I use? Yes, very good. I equals. Very good. Tell me your name. Luisa, where are you? Yeah. Tell me your name so I will remember you. Well, I don't see you. Where are you? Okay. See, I'm partially blind. Okay, I have to put those special glasses. Okay, so current is by definition charges coulomb per second. So you have 170 equals Q, that's my unknown, over time. Okay, is that right? So Q, you cross multiply divide equals uh, 612,000 coulomb. Okay, how much energy does the battery deliver? So energy equals 1 equals the energy. What did you say? Energy. So I forgot. Yes. So voltage equals energy per charge, right? That's what it is. So the voltage equals energy per coulomb. Yes? Is that clear? So we have the energy equals the voltage times Q. There is a different way to do it also. But okay, so energy equals V times Q. We can go back to here. Okay, energy is voltage times Q. Or we can say also that energy is power times the time. So energy will be, voltage is what? 3 times 6, 12,000 joule. Okay, so that's going to be the energy in joule, because joule is a very small unit of energy. No, I did a mistake here. Nobody tells me anything here. What did I? It could not be those big number, right? Could not be that number. So how much is in amps? So 1,000 milliamps is 1 amp, right? So 0.17 milliamp. How much is that in amp? You have to divide by 1,000. Wait. 1, 2, 3. Okay, so that's why we found those crazy number. So this one is 612, isn't that right? So that will be 1, 2, 3, 4. So it's going to be 1.7 times 10 to the negative 4. So you get 612, isn't it? So 3, 6 times 1.7 times 10 to the negative 4. So it's going to be what here? Yes. Okay. 0, I'm going to do that. 0.612 coulomb. Is that right? 0.17 divided by 1000 times 3600, 0.612 coulombs. Okay, no, because that was a big number, I say. Something is wrong. 0.6112, and what do you get? Yeah, that's better, Joule. Right? Is that clear? Is that right? Do you all get that? Yes? The other way to do it, you could find the power, which is voltage times current, and then you say that the energy is power times time, okay? And you will get the same thing. Conclusion, 1 amp is 1,000 milliamp. Okay, so I'll let you do it the next. Make sure I don't messed up. So this is based on what true. This is true, okay? I checked my laptop, not the laptop I have today, but at the time, the voltage drop across a laptop is about 20 volts. Okay, so it means you have in your charger, you have a way to turn 120 into 20. And then the laptop does not like AC. So inside your charger, you have a way to turn AC to DC. If you have AC in your laptop, you're going to destroy it. It doesn't like that. So the voltage drop across my laptop to make it work is 120 volt, okay? 20 volt. And I'm going to do it like this. So that will be the voltage and that will be the current. So I look at my charger, which is not here, and it says it needs 1.5 amp and it needs 20 volt. So then you can find what is the amount of energy consumed by your laptop. So the power will be what? Yes, 30. You're right, because you multiply voltage times current. So that's going to be 30 watts. Okay, or 30 joule per second. So I'm using the equation power is voltage drop times the current. So you see you have my laptop here. So here you have 2 points here. Those 2 points has to be 20 volt. And then you have electricity flowing inside the laptop and it has to be DC. So this is connected to a charger and the charger makes sure that here it's a plug. Okay, so here you have 120 volt AC. Turn that into 20 volt DC. And the current here is 1.5 amps. Is that clear? Okay, B. What is the energy consumed in 24 hours? So you have the energy in 1 second. So 1 hour is how many seconds? Very good, 3600 seconds. So the energy total consumed in 24 hours, so it's 1 day, That's going to be 30. What do I do? I multiply, right? 24 times 3600, right? Okay, so it's going to be 30 times 24 times 3600, and you get a big number. Is that right? So it will be 1, 2, 3, 4, 5, 6. Okay, joule is a small unit. Is that right? So joule per second, so 30 watts. So when you buy, for example, a laptop, it says sometimes it will give you the voltage, it will give you the watt and not the current. Or it will give you the voltage and the current and not the watt. So now you know how to do it, okay? So 30 joule per second, you have 3600 seconds in 1 hour, and you have 24 hours. Is that right? Okay, so the amount of charge flowing in 1 hour. So the amount of charge flowing in 1 hour. So you have the current here is 1.5 amps, which means 1.5 coulombs per second, right? Or you can go back and look at the equation here. Well, all my equation, you see I equals Q over T. You can do that too. So you can use the equation I equals Q over T. Okay, so you have 1.5 equals Q over 1 hour is very good. Okay, so you can find Q. I'm going to go here. So 3600 times 1.5. Yeah, right. Say that. Yeah, what's your name? Hmm? Ariel? Okay. Tell me after. Not only I'm partially blind, but I'm partially deaf. So Coulomb, come to see me after. So 5400 Coulomb. Find the energy in kilowatt hour consumed in a day. So this is something we didn't do yet, but kilowatt hour is a unit for energy. Okay, so remember energy, okay, it's power times time. Do you agree with that? Okay, because power is energy divided by time. So if the energy is in joule, if the power is in watt, and the time is in second, then you're going to have joule. Okay, so joule, the amount of energy consumed, equals to power in watt, time in seconds. So let's answer that question just with your guts. Now I want the energy in another unit called kilowatt hour. Okay, so if you look at your electric bill, they will charge you and they find the amount of energy you consume in kilowatt hour. So that means you still have power, you still have time, the equation does not change, but what's going to be the unit for power? Kilowatt. What's going to be the unit for time? Hour. Okay, it's just a different unit of energy. So you have joule and you have kilowatt hour. Okay, so do we have the power? We have the power here. So let's find what is the energy consumed in a day. So 24 hours. Okay, so I'll give you some time so you can talk to each other. It's a different unit of energy. Cannot make my eraser bigger.
I think if you click on the eraser itself, I think there's like a large eraser.
But yeah, but it doesn't work. Usually it works. I don't know why. I don't know. Things are strange. Okay, so the energy in kilowatt hours, it's a unit of energy, equals to the power in kilowatt times the time in hour. And let's review from physics 1. 1 kilo is how many? 1,000, right? Like you make, I don't know, 50K, that means 50,000, right? So what's the power? 30. So first you convert that in kilowatt. So that means uh, 1, 3. So 30, you go back 1, 2, 3. So it's going to be 1, 2, 3. Do you agree or no? So if you don't agree, you say that okay, 1 kilowatt is 1,000 watt. So 30 watt is how much? Okay, so you do 30 divided by 1,000. So 1, 2, 3. Do you agree now? Okay. 24, where are we? In a day. So in hour, how many hours in a day? 24. Okay, so we will do more problem like this times 24, and you get kilowatt hour. So you see, it's very small. And in, I think in Miami, I think it's 16 cents per kilowatt hour or something like this, or 15 cents per kilowatt hour. So even if you plug your laptop and it's on all day long, you're not going to pay much, okay? You don't want to do that with a hair dryer or a microwave, of course, because the power is uh, like 1,000 more or something like this. In the New York State. So that's how old I am, because now it's not 18 cents anymore. It must be like 20 cents, something like this. So if you want to know how much you're going to pay, okay, so let's say you are in Miami, it's 60 cents per kilowatt hour. All you have to do is to multiply. Yes? Okay, so let's verify. Look at that. See, I pay my bill 15 cents per kilowatt hour. So once you know that, you can, for example, say you have an AC unit, you look at the power on it, okay? And you say how much kilowatt hour I'm going to consume in one day. So you can predict how much it's going to cost you per day, how much it's going to cost you per month. And in New York, let's see, New York City, 21, okay? And I think one of the worst, I think it's Alaska. 20. So don't move to Alaska, okay? Unless you can take the cold. Oh, Hawaii. Oh, Hawaii. Oh, let's check Hawaii. Um, what does it say? It doesn't say so much. So much. 32. Look at that. It's huge. Okay.